Hey everyone, welcome back, and let's write some more neat code today. So today let's solve edit distance. So this is a dynamic programming problem, and this is very similar to the problem longest common subsequence, which is a problem I've solved on this channel. So this problem is basically an extension of that problem. So we're given two strings, word1 and word2, and our goal is to return the minimum number of operations required to take word1 and convert it into word2. And we only have 3 operations available to us: inserting a character into word1, right? Remember, because we're trying to take word1 and convert it into word2. We can't change word2. We can delete a character from word1 because we can't change word2. And we can replace a character in word1. And so replacing a character is basically changing one character into another. So in this case, there's 3 operations it would take to take horse and turn it into this string. Of course, we'd want to get rid of the H, right? But we would do that by replacing the H with an R. So this is going to be an R. And then we have 2 R's, right? So we'd get rid of this R. So we get rid of that. And lastly, we see we have ROS, we have an extra E, so we're going to get rid of the E as well. So we did that in 3 operations, so we can return 3. So first of all, let's analyze some simple cases. What if we had the case where word1 and word2 were both just empty strings? How many operations does it take then to take word1 and convert it into word2? Obviously 0, right? We don't have to do anything. They're already the same. Similarly, if word1 was, let's say, ABC, and word2 is also ABC, we also don't have to do anything, right? We'd look at the first character, see, oh, they're the same, right? Since they're the same, of course, we don't have to consider them anymore, right? Then all we have to do is compare the remainder of each string, right? But then we see again, hey, B is the same, good. C is also the same, good. And look, perfectly timed, there's no characters left in word1 and there's no characters left in word2. Therefore, 0 operations were needed, right? What if word1 was ABC and word2 was empty? Then what would we do? Is it even possible to take this word and then convert it into an empty? Of course it is. In this problem, it's always going to be possible to take word1 and convert it into word2, right? Because we can insert a character, we can delete a character, or we can replace a character. So it's always going to be possible because in the worst case, right, this is what we could do. We could take every single character in word1 and just delete it. Delete that, because none of these show up in word2. Just delete all of them. If there was some character, maybe there's a Z over here, then we could just copy every character after we've deleted these and then copy it over here, right? Add that Z, but no, we don't need to. So my question to you is, if word2 is empty and word1 is non-empty, then this is a base case, how many operations is it going to take? It's always going to take the length of word1, whatever the length happens to be, because we're going to have to delete every single character, right? So that's one base case. Word2 is empty. What about the opposite case? What if word2 was ABC and word1 was empty? Is this possible? Is it possible to take word1 and convert it to word2? Of course it is, right? Because we're allowed to insert characters in here. So basically we could just read character by character. A, add that here. B, add that here. C, add that here as well, right? So we can just copy every character. So my question to you is, in this case, the opposite case, where word2 is non-empty, but word1 is empty. How many operations is it going to take? Well, we're just going to copy each character in here, right? So in this case, it's going to take the length of word2. That's how many operations it's going to take, right? So basically what I'm getting at is, if word1 is empty and word2 is non-empty, then we're going to return the length of this as the minimum number of operations. If the opposite was true, right, maybe this is empty but this is non-empty, then we'd return the length of the non-empty one. If one of them is empty, we're going to return the length of the non-empty string. That's going to be the minimum number of operations. This is important because this is our base case. So now let's try to brute force this. How are we going to handle it? Well, we're going to have 2 pointers, right? We're going to have one pointer pointing at a character in word1 and a second pointer pointing at a character in word2. We're going to compare character by character. So the one case is, what if they're exactly equal? Then what is the sub problem then, right? Because we don't have to consider these characters anymore. Now we're dealing with the sub problem of the remainder of those strings. So basically, if I'm calling the pointer in word 1 I and I'm calling the pointer in word 2 J, if these characters are equal, that means we can basically say I plus 1 is the new problem and J plus 1 is the new problem in word 2, right? So we're just shifting our pointers like that. So basically, to summarize, if these characters are equal, right, at the I and J pointer, basically what I'm saying, the characters are equal, then we're just going to increment I by 1 and increment J by 1. The number of operations we had to do was exactly 0, right? We didn't have to do anything. They were already equal. We didn't have to modify word 1 at all. To the next character, so our I pointer is going to be over here, our J pointer is going to be here because we incremented both of them by 1. So now let's compare the characters. C and B are not equal, right? So now our else condition is going to execute, and we don't know. We know we have 3 options. We can insert a character, delete a character, or replace a character from word 1, but we don't know which one to do, right? So let's just try all 3. What happens if we insert a character? What character are we going to want to insert over here? Obviously, we'd want to insert the character from word 2. We don't know if that's going to end up making word 1 exactly into word 2 in the minimum number of operations, but let's just try it and see what happens, right? So what would we do if we inserted a C over here, right? We're not deleting a character. All we're doing is inserting a C over here. In that case, our I pointer is still going to be pointing at this B, right? But since we inserted a C over here, it's hard to read, but let's say I inserted a C in between over here, that means we took care of the C from word 2, right? So basically, we don't need to find a matching C for it anymore. We do need to find a matching B somewhere over here, right? So we're going to leave our I pointer where it is, but we're going to take our J pointer and then shift it to the next position in word 2. That's what we would do if we inserted a character. So as you can see, when we insert a character, we are taking one operation, right? So we're going to have to add a 1 to the number of operations we did. But when we shift our pointers, the I pointer stays the exact same, but J is incremented by 1. So that's one possibility. Another possibility is we delete a character. So we're allowed to delete characters from our word 1, right? So what would happen if I just deleted this character? What we're saying is, okay, I can't find a matching C in this position, right? And we don't have a B corresponding to that position. So I'm just going to ignore this guy and hopefully the remainder of the strings can match up, right? So what I'm saying is I'm going to take our I pointer and yes, I am going to shift it to the next position because I want to pretend like this character never existed. But it does take one operation to complete that. But since we did not find a matching C yet, right, we have to leave our J pointer here, right? We have to keep searching until we find a matching C. Ultimately, we want word 1 to match word 2. So in this case, for the delete operation, what we're saying is I is going to be shifted, but J is going to stay the exact same. So I plus 1, but J stays the same. As you can see, this is, kind of a pattern. We're starting to see a pattern, right? And the last thing that we can do is replace a character from word 1 that shows up in word 2, right? Obviously, if we're replacing a character from word 1, right, we're going to want the character that's matching in word 2, right? So what we'd want to do is take this B and replace it with a C character, right? If we did that, clearly these two characters match, right? We made them match. We forced these characters to match. So in that case, we know that the C has a matching C up here. So we can take this I pointer and shift it, and we can take our J pointer and shift it to the next position, right? So the replace actually ends up doing the exact same thing as if the characters were equal, and that makes sense because what we're doing is we're forcing them to be equal with the replace operation. The difference between the replace and if they were already originally equal is that the replace does take a single operation. If they were already equal, the number of operations it takes is 0, right? So it does come with a cost, even though replace is pretty powerful. As I said, with replace, what we're going to do is increment I and increment J. So let's just go with the replace operation because that's actually going to end up being the minimum solution. So now we shifted our pointers to the next position. We see D and D, they match each other. So this is the statement that's going to execute. And we know that takes 0 operations, right? So we're going to increment both pointers by 1. J is going to be over here now. I is going to be over here. Notice now how we have two empty strings. Remember the base case, if both strings are empty, we can return 0 because it takes 0 operations to make them equal, right? They're already equal, so we're done. We return 0. How many operations did it take, by the way? If you were counting, we did have to execute a single replace operation. That took 1 operation, so the result is 1. So we are noticing that the sub-problems are good to solve before we try to solve the original problem of comparing the entire lists. Let me reformat this into the dynamic programming explanation. So you may have seen something like this before. This is going to be a two-dimensional dynamic programming problem. It's good to visualize it kind of like this. So what we're doing here is we are comparing these two strings, and for this position, this is what we want to calculate. In this position, what we're going to do is we're going to store basically the minimum number of operations for these two strings, starting at this character for word 2, starting at this character for word 1. So basically the entire strings is going to be stored here. What would be stored in this position, basically corresponding to here? So we're comparing these two, basically the remainder of this string, and from here the remainder of this string. So in this position, what we would store is the minimum number of operations it would take to make this sub problem, these two substrings, how many minimum operations it would take to make them equal. Okay, so that makes sense so far, but then why do I have this extra layer over here? This portion is for our base case. What would be over here, right? So clearly we see that there's an empty string over here, there's an empty string over here. What value should I put over here? Obviously 0, right? Two empty strings take 0 operations to make equal. What about in this position? What does this position tell us? Well, we have an empty string from word 2, but over here we have the entire string from word 1. So how many minimum operations would that take? Remember, we went over that at the beginning, and it would just be the length of the non-empty string. So here we can see the length of the non-empty string is 3. What about in this position? Similarly, word 2 is empty. Word 1 has a length of 2, so we'd put 2, and basically continuing to 1 and then down to 0, right? So similarly over here, we have an empty string from word 1. Word 2 is completely full, and the length of it is 3, so we're going to put 3 here, and then continue just counting down. 3, 2, 1, right? So in what order are we going to solve this? If we start at the beginning, then we're going to notice something. Notice, okay, well, we're comparing these two characters in this position, right? They're both equal, right? So then we're going to execute this statement, right? So we're going to take I plus 1 and J plus 1. What does that tell us? That tells us that the result of this value depends on this value, right? So, okay, then let's take a look at this value. Well, in this case, they're not equal. B and C are not equal. So then what are we going to do? Remember, if they're not equal, we have to brute force it. We have to take a look at all 3 operations. And remember, I corresponds to word 1, J corresponds to word 2. So in the insert operation, what we're going to do is look in this spot. In the delete operation, what we're going to do, increment I by 1 in this case, so we're going to look in this spot. And for the replace operation, we're incrementing both of them, so then we're going diagonal again. From this, since we have 3 values that we're looking at, what we're going to do is we want to know which one of these 3 leads us to the minimum number of operations, right? So what in reality, what we're going to do is, since we're noticing that it depends on the lower values, let's do this bottom up. This is called bottom up dynamic programming. We're going to start at the bottom, compute this value, compute this value, compute this value, and then so on and so on, and then work our way backwards until we finally get to the result. And notice, if we do start in this position, we already have the values that it could possibly depend on, because those are our base cases over here, diagonally, and below, right? And so notice D and D are equal. So what we're going to do is from here, we're going to look at the diagonal value, right? Because this statement is going to execute. We're going to see it's 0. So that's what we're going to put over here. And then eventually we would compute these, and then eventually we would get up over here, right? And we'd compute the value from that. And then eventually we'd get all the way up here, and we would compute the value from here. You would see that we'd end up putting a 1 over here. We'd end up putting a 1 over here. So what would the value over here end up being? Well, let's look at the two characters, D and C. They're not equal. So what we're going to do is we're going to look down, we're going to look diagonal, and we're going to look to the right. Which one of those values is minimum? It's over here. So that's 0, but we do have to add 1 because in this case, we do need to do a single operation. So we add 1. And similarly is what we would do for every single position. You know, we'd compare the characters and then we'd execute this statement or we'd execute this statement. So I'm not going to run through that, but I think this is simple enough that if you want to, you can get a piece of paper out and then try it for yourself and you'll probably come to the same conclusion. So with that being said, let's jump into the code. This is exactly what I'm going to do with the code. I'm going to have a 2-dimensional array and I'm going to execute these exact statements. So I'm going to call our 2-dimensional array our cache. And so basically I'm going to initialize it to initial values of just max integer or float infinity in Python. And you can probably initialize this any way that you would like in your own language. There's probably different ways that you'd want to do that. But I'm going to use a list comprehension. So basically I'm creating a list with float infinite as the value of length word2 plus 1. Remember, because we do need to make our 2-dimensional array a little bit bigger to handle those base cases. For this list, I'm going to have one of these lists basically for every character in the range of the length of word 1. So this probably looks confusing if you're not familiar with Python, but basically I'm just creating a 2-dimensional array with these dimensions. Actually word 1, the length of word 1 plus 1, because remember we are worrying about the base case, but basically yeah, a 2-dimensional array. So now I want to fill up our bottom row of the 2-dimensional grid. So what I'm going to do is for our cache, I'm going to go to the bottom row. What's the bottom row? It's going to be the length of the word 1. And that's going to be the bottom row, and we're going to go through every value of it. So for every j of that, remember it's going to be basically in descending order. So what I'm going to do is, and it's going to initially start at the length of what word 2 happens to be, because remember the base case is if one string is empty and the other string isn't. So word 2, and it's going to basically be decrementing by 1 each time. So what I can just do is just say length of word 2 subtracted by j. And actually, I keep forgetting the bottom row is actually not just going to be length of word 2, but it's going to be length of word 2 plus 1. So I want to make sure to add that plus 1. And similarly, what we're going to do is, and for that rightmost column, what we're going to do is go through every position in it. So length of word 1 plus 1. And for every position in the last column, and the last column can be found like this, basically for every I in the last column, which is going to be length of word 2 in this case. And what we're going to do is similar to what we did up here, take what the original length of word 1 is, and each time subtract it by an additional value. Basically, we can use I in this case. So this might be a little bit confusing. You can do this a bunch of different ways. If this is confusing to you, you can probably find your own way to do it. But basically, we're just initializing the base case of our 2-dimensional array. But so now let's actually get into the dynamic programming portion. So remember, this is going to be bottom up. So we're going to work our way backwards from the length of word 1 minus 1. And the reason we're minusing 1 is we know we already filled up our base case portion. So now we actually want to get to the actual dimensions of our 2 strings. And we're going to do this in decrementing order until we get to the beginning, until we get to the 0th index, which is when this is going to end up stopping. And similarly, let's work our way backwards from the length of word 2. So we're going to start at the bottom row and work our way backwards and then keep doing that until we end up getting to the top row. And remember, we had 2 cases. Either word 1 at index I is equal to word 2 at index j. Basically, the characters that we're comparing are equal, or they're not equal. Remember, if they are equal, then that's really easy for us, right? Because then we can just say, okay, cache of position ij, what we're doing here is computing what's the minimum number of operations it would take to get the substrings starting at I and the substrings starting at j for these respective words. Compute the minimum number of operations, so we can get that in this case, since the characters are equal, just by saying cache of I plus 1, cache of j plus 1. And the else case is where we have to check all 3 directions and then take the minimum of those. So what I'm going to do is say 1 plus the minimum of those 3 directions. So cache of I plus 1 and leave j the same, and Also, we want to take the minimum of cache of I left the same, but j plus 1. And last but not least, we want to take the minimum of cache of I plus 1 and j plus 1. So this is a long line, but I'm going to leave it as it is. But yeah, basically this is taking care of insert, delete, as well as replace. And it's taking the minimum of whatever those were, adding 1 to it because we are having to do at least one operation, whichever one of those it is, and then storing that minimum here. And once we have done that, once we've filled up our entire two-dimensional array, we want to return the value at index 0, 0 of our cache, because that tells us what's the minimum number of operations for the beginning of both strings. So basically the entirety of both strings. So this is definitely a doozy of a problem. It's not a ton of code, but it does take some thought to get to here. And it's definitely an extension of longest common subsequence. So I recommend solving that problem if you haven't already. But I do hope that this was helpful. It's a tough dynamic programming problem. If it was helpful, please like and subscribe. It supports the channel a lot, and I'll hopefully see you pretty soon. Thanks for watching.